Welcome back to the deep dive. We are back with another stack of research, and today is going to be a little bit different.
Hmm.
Usually we're looking at something cutting edge or maybe a geopolitical shift or, some new tech trend. But today we are looking backward.
Way backward.
We are engaging in a bit of time travel today,
We really are.
and we are looking at a system, a piece of technology really that you probably see every single day of your life, but you almost certainly take it for granted.
Oh, for sure.
I want to start with a visual just to sort of set the scene.
Go for it.
Okay, picture the year we're in right now, the current year.
Okay, got it.
If you see it written on your phone or on a calendar or, I don't know, in a spreadsheet, it's just data. It's 4 digits.
Right.
2026.
Functional.
It's functional. It tells you where you are in the timeline.
Right.
But if I ask you to picture that same year carved into the cornerstone of a massive bank building, or maybe flashing on the screen at the very end of some moody film noir,
Then it transforms. It becomes MMX6.
MMX66, and suddenly it feels different, doesn't it?
Oh, completely.
It doesn't just feel like a date anymore. It feels
Heavy.
Heavy, exactly.
Yeah.
It feels permanent. It feels like it has weight to it.
It really does.
We're talking, of course, about Roman numerals. And I have to admit, when I first looked at the packet for this deep dive, my first reaction was, okay, cool, but is there really an hour of conversation here?
Laughs.
Yeah. I mean, I learned this in 3rd grade. I is 1, V is 5, X is 10, done.
That's the standard reaction. We all think we know it because we learned the code.
Right. But looking through the research, specifically this huge historical overview we've pulled from the archives, the story of these numbers is just so much weirder.
Yes.
It's so much messier and, frankly, so much more chaotic than I ever realized.
It really is. It's one of those topics where the school version we all learned, the neat little chart on the chalkboard, is basically a myth.
A myth.
Or if not a myth, it's a kind of polite fiction. It's a modern cleanup operation of a system that was historically anarchic.
Anarchic is a strong word for numbers.
But it fits. I mean, we tend to think of the Romans as these rigid, disciplined engineers.
Straight roads, square legions, strict laws.
Exactly. So we assume their numbers must have been just as rigid. But the reality is the way they used numbers was incredibly flexible.
So our mission today is to strip away that 3rd grade myth.
Let's do it.
We're going to look past the Super Bowl logos and the movie copyright dates and really try to understand the machinery. We're going to find out why the Romans essentially ignored their own rules.
Mm-hmm.
Discover a secret system of fractions based on the number 12, which, spoiler alert, is why we have the word inch.
That's a great little detail.
And figure out how on earth you build an empire without a zero.
That zero question is the one that really trips everyone up. It's like the cognitive gap between us and them.
It is. So let's dive in. I want to start with the rules versus reality, because this is where the biggest shock was for me.
Okay, let's do it.
Let's go back to that classroom. If I walked into a 3rd grade class today, or even just grabbed a random person on the street and asked them to write the number 4 in Roman numerals, what do?
Oh, they would almost certainly write IV.
Eh.
An I followed by a V.
And if you ask them why, they'd recite the rule we all know, right?
Subtractive notation.
Subtractive notation.
Right. The logic is simple. You can't have 4 I's in a row because it looks clunky. It takes up too much space.
So the rule says you place the smaller value before the larger value to indicate subtraction. 5 minus 1 equals 4.
It's elegant. It's clever.
It is. And it's the standard we use today.
Hmm.
If you look at a textbook or a standard conversion chart on Google, that is the rule. But here's the first big shock from the historical record.
Yeah.
The Romans almost never did that.
Rarely. They just didn't.
They didn't use RV.
Very rarely. I mean, for the vast majority of Roman history, and certainly for the casual user, the shopkeeper, the soldier, the stonemason, the number 4 was the third.
Just 4 lines?
4 vertical strokes?
Yeah. So the strict rule against 4 identical symbols in a row, it just didn't exist.
It's largely a modern stylistic preference that got kind of, retroactively applied as a law.
Huh.
Think about it from the perspective of someone living in 100 AD. You aren't a mathematician. You're counting bushels of wheat. 1, 2, 3, 4. It is cognitively much easier to just make 4 marks than to perform a sudden subtraction operation in your head.
That makes a lot of sense. Subtraction requires foresight. You have to look at the V, realize there's an I before it, and then calculate.
Right.
But 4 lines is just 4 lines. It's a tally.
Exactly. It's visual versus abstract. And we have hard evidence of this carved in stone. We aren't just guessing.
Okay, where?
The most famous example is the Colosseum, the Flavian Amphitheater.
Right. So help me visualize this. We're in Rome, 1st century AD. The Colosseum has just opened.
It's this massive structure. It holds, what, 50,000 to 80,000 people. It's the Superdome of antiquity. Now, just imagine the chaos of getting 50,000 people into their seats.
It's hard enough getting into a concert today with a QR code.
Exactly. So to manage the crowd, the Romans had a system. They had 80 entrance arches on the ground level.
Okay.
And each arch was numbered so the spectators could match their ticket, which was a pottery shard to the gate.
Just like finding section 101 gate A.
Precisely.
Yeah.
So if you go to Rome today, you can still walk up to the Colosseum and see these numerals carved above the arches. They're weathered, but they're legible. Gate 23 is marked XA3.
Standard stuff.
Gate 52 is IL4. But if you walk around the perimeter to gate 44...
Edge, according to the school rules, should be XLV, XL plus 4.
You'd expect that. But on the stone, clearly carved by a Roman artisan, it says XL3.
No way. So they mixed the systems.
Yep.
They use a subtractive method for the 40, the XL, but they use the additive method, the 4 I's, for the 4.
They did. And that tells us something really profound about how they viewed these numbers. They weren't following some rigid syntax like computer code where a syntax error crashes the program.
Right.
They were using whatever was clearest to read at that magnitude.
It's just pragmatic. XA3 leaves no room for doubt.
Right. And this preference for the 4 I's actually survived the fall of Rome. It survived for thousands of years. We see it everywhere today, but most people never notice it.
You're talking about clocks.
I am. Have you ever really, scrutinized a grandfather clock? Or even a nice wristwatch with Roman numerals?
You know, I check the time, but I don't think I've ever audited the typography.
Well, next time you see a traditional clock face, look at the 4 o'clock position. It is almost universally 4-3.
Really?
It is very, very rare to see a phi on a clock face.
What about Big Ben?
Big Ben is actually the exception. That's the one people point to. Big Ben uses the 4th. But most other famous clocks use the 3.
But why? If we know 4 is the correct number 4, why do clockmakers insist on the 4 lines?
It comes down to aesthetics. It's all about visual balance.
How so?
Okay, picture the circle of the clock face. You have 12 numbers arranged in a circle.
Yeah.
If you use third for 4 o'clock, look at what happens to the symmetry. You end up with these 3 distinct groups of 4 numbers.
Okay, break that down for me.
So the first 4 numbers are 1, 2, 3, 4. If you use 3, then all 4 of those numbers use only the symbol I.
I, there, 3, 3. Okay, I see that. It's the I quadrant.
Exactly. Then the next 4 numbers, 5, 6, 7, 8, they all involve the V symbol. V, 6, 7, 8. That's the V quadrant.
And the final 4, 9, 10, 11, 12 all involve the X.
Got it. 9, X, LF, 12. It creates this beautiful radial symmetry. 3 groups of 4.
That is surprisingly satisfying. I've never thought of that.
It gets better. Visually, 3 is a heavy number. It has 4 strokes. It's wide.
Okay.
On the opposite side of the clock face is the number 8, 8. That is also a heavy, wide number, 4 characters.
So 3 balances 8.
Correct. If you use 4, it's a skinny number, 2 characters. It would look lopsided across from the big, heavy 8. The clock would look like it was tilting to the left.
That is amazing. It's typography winning over mathematics.
Typography winning over mathematics is actually a great summary of Roman numerals in general.
Wow.
They are graphic symbols first and mathematical tools second.
But the chaos goes deeper than just the number 4, doesn't it?
Oh, yeah.
In the research, there was this part about the IRX notation that absolutely broke my brain.
Ah, yes. The 18th Legion.
This sounds like a sci-fi movie, the 18th Legion.
It was a very real, very famous Roman military unit. Now, if you or I were to write 18 in Roman numerals, we'd write 8th.
10, 5, 3 ones. Simple addition.
Right. But we have historical records, monuments, and markers left by the Legion themselves, where they identified their unit as the IRX.
So IX.
Which reads as 2 subtracted from 10, or I guess more accurately in the full context, 2 subtracted from 20.
Wait. I thought the rule, even if we ignore the third thing, I thought the rule was you could only subtract 1 digit. You can do IX for 9, but you can't do IX for 8.
In the standardized modern version, you absolutely cannot. If you did that on a math test, you'd fail. But the Romans didn't care about our tests.
So what did they care about?
They cared about their language.
It's linguistic.
It's entirely linguistic. The Romans spoke Latin. And in Latin, the word for 18 is duodevigenti.
Okay, let's parse that.
Duo means 2. D means from. Vigenti is 20. The word literally means 2 from 20.
Oh, so when they wrote IIXX, or shorthand IIX, They were just transcribing the way they spoke. 2 before 20.
Exactly. So like if we wrote the number 19, not as a 1 and a 9, but as 120, they were writing the words using the symbols.
That is fascinating. It explains why the rules felt so fluid. They weren't checking a rule book, they were just writing down what they said.
We see the same thing with the number 98. Sometimes they wrote it as Ikai.
2 from 100.
Yes. Instead of the standard XVH, 90 plus 8, they just said it's 2 away from 100, I. Much easier.
It makes the system feel so much more human. It wasn't an abstract code, it was shorthand for speech.
It was a living system. And because it was living, it mutated. It wasn't static. Even into the 20th century, we see architects and designers ignoring the rules for aesthetic reasons.
You mentioned the Admiralty Arch in London in the notes. That's a fairly modern building, relatively speaking, 1910.
1910. Now, how do you write 1910 in standard numerals?
Okay. M for 1,000, CM for 900, X for 10, MCMX.
Short, punchy, 4 characters.
Right.
But if you look at the Admiralty Arch, inscribed in massive letters across the top, it says MDCCCCX.
MD and then 4 Cs.
4 Cs. 4,500 plus 4 100s. Again, avoiding the subtractive CM form.
But why? Just to make it longer.
And yeah, the prevailing theory is exactly that. The architect wanted the inscription to be wider. He had a big arch to fill. MCMX is too short. It looks dinky.
Lofts.
MDCCCX takes up more physical space on the stone. It looks grander. It matches the scale of the building.
So you can just stretch the number to fit the architecture?
Apparently so. If you have a chisel and a hammer, you make the rules.
That's a powerful position to be in. But sometimes these variations aren't aesthetic choices. Sometimes they're just straight up mistakes.
Oh, yeah.
And the research had this incredible story about a movie copyright.
Oh, this is a classic. The movie is The Last Time I Saw Paris.
MGM movie, 1954, Elizabeth Taylor.
Great film. Now, at the end of every movie, you see the copyright notice. It's usually the very last thing on the reel.
Right, Roman numerals.
And 1954 should be written as MCMLIV. M for 1,000, CM for 900, L for 50, IV for 4.
Okay.
But the title artist, the person painting that card, messed up. They wrote MCMXLAV.
Let me decode that. MCMXLV, that's 1944.
Exactly. They accidentally wrote 40 XL instead of 50. They dated the movie 10 years before it was actually made.
Does that really matter? I mean, everyone knows when the movie came out. It's in the newspapers.
It matters for copyright law. Especially back then, U.S. copyright terms were strictly based on the date in the notice.
Oh, no.
By printing an earlier date, they theoretically shortened their copyright term by 10 years.
That is a very expensive typo.
It is. And there was a genuine legal question. Did the error invalidate the copyright entirely? Because the notice was defective.
That is wild. A typo in a dead numbering system could cost you the rights to your movie.
Fortunately, the courts usually rule that if it's an honest mistake and doesn't harm anyone, you don't lose the rights. But it highlights the danger of using a prestige system that nobody really speaks fluently anymore.
It's like getting a tattoo in a language you don't speak. You might end up with soup written on your arm instead of strength.
Exactly. It's a risky aesthetic.
I want to pivot a bit. We've talked about how the numbers are used or misused and the flexibility of the rules, but I want to go back to the very beginning.
Okay.
Where did these symbols even come from?
The origin story.
Because the story I always had in my head is that they're letters. M is for mil, 1,000. C is for centum, 100. So I just assumed the whole system was an abbreviation of Latin words.
That is the common belief. And it makes perfect sense, which is usually a sign in history that it's wrong.
Lasses, of course. Nothing is ever that simple.
The M and C connection is actually a happy accident or a convergence that happened much later. The true origin of Roman numerals isn't the alphabet at all.
Then what is it?
It's tally marks.
Tally marks, like scratches on a prison wall.
Or notches on a shepherd's stick.
Yeah.
Imagine you're an Etruscan shepherd in Italy, maybe 500 BC, before Rome is really Rome.
Okay.
You're out in the field counting your sheep.
I'm in the field. I have a stick and a knife.
Sheep 1 comes by. You cut a vertical notch.
Yeah.
I, sheep 2, notch 2, sheep 3, notch 3.
Simple.
But when you get to, say, 8 or 9, counting those little identical lines becomes a nightmare. Your eye glazes over. You can't tell at a glance if it's 8 or 9. You need a way to group them, a checkpoint.
Like how we use the diagonal slash when we do tally marks on paper today.
Yeah.
We do 4 lines and then cross them out to make a bundle of 5.
Exactly. That is a universal human impulse. So the theory is on the 5th notch, the shepherds didn't just cut a line. They made a double cut to distinguish it. If you cut 2 lines meeting at an angle, what shape do you get? AV. So the V isn't the letter V. It's a graphic representation of a check mark or a notch on a tally stick.
That is so much more intuitive than V is an arbitrary letter.
And then you keep going, 6, 7, 8, 9, and you hit 10. You need another checkpoint. So you do two Vs, one upright and one upside down, meeting at the points.
Which makes an X.
Precisely. So I, V, and X are essentially pictures of cuts in wood. There is another theory that relates it to hand signals. Holding up 5 fingers makes a V shape with the thumb and forefinger, but the tally stick theory is very robust archaeologically.
Okay, so that explains the small numbers. But what about the big ones? L, C, M. Surely M is mil.
This is where it morphs from tally marks to paleography, the study of old handwriting. Let's take the symbol for 50. Originally, it wasn't an L. It was a symbol that looked like an arrow pointing down or an inverted T.
Okay, I'm trying to picture that.
But over centuries, scribes writing quickly on wax tablets or papyrus started to curve the line. The bottom stroke flattened, the right side curved up, and it started to look like an L.
So it just drifted into the letter L because of lazy handwriting?
Efficient handwriting.
Yeah.
And the M is the best story.
Tell me about the M.
Originally, the Etruscan or early Roman symbol for 1,000 was a circle with a cross inside it, or sometimes a circle with a vertical line through it. Imagine the Greek letter phi.
Okay, a circle with a line.
That symbol is hard to write quickly. It's like lift your pen, draw a circle, draw a line. So people got lazy.
Blast.
They stopped closing the circle. It became two curved humps, like a sideways figure 8 or an infinity symbol.
Which looks a bit like a curvy M.
Right. And here's the kicker. Because the Latin word for 1,000 happened to be mil, the Romans saw this curvy symbol evolving and said, hey, that looks like an M. And M stands for mil. Let's just use M.
So it's a back formation. They rationalized the symbol after the fact.
Exactly. It's evolution, not intelligent design. They fit the symbol to the word later on.
It's amazing to think of this system evolving from shepherds cutting sticks in a field to being carved into marble monuments. It feels so organic.
It is. It's a very human system. It relates to hands, tallies, spoken language, which explains why it lacks some things that we consider essential in math today.
Which brings us to the biggest missing piece, the elephant in the room.
Is zero.
How do you build an empire, engineer aqueducts, and conquer the known world without a zero?
It's a great question. And the answer lies in the difference between a positional system and a non-positional system.
Break that down for us.
So in our modern Arabic numerals, the position of a digit tells you its value. In number 2026, the 0 is doing heavy lifting. It's a placeholder telling you there are no hundreds.
Right.
If you take that 0 away, you have 226. The number collapses.
The 0 holds the structure. It keeps the 2 in the thousands column.
Exactly. But Roman numerals are non-positional. The symbol X always means 10 no matter where it sits. You don't need a placeholder to tell you there are no hundreds because you just don't write any hundreds.
You just skip it.
You just skip it. If you have 2026, you write MM 2000s XX 20 VI 6. You don't need to say N0 hundreds. The symbols carry their own value independent of a column.
So they didn't have a symbol for 0 because they didn't need it for writing numbers.
Right.
But did they understand the concept of nothing?
Philosophically, yes. They had the word nulla, meaning none.
Right.
And interestingly, medieval monks, who were the main users of Roman numerals for 1,000 years, sometimes used the letter N for nulla to signify 0 in tables.
Like a shorthand.
Yes. But it wasn't a number you calculated with. You couldn't do 5 times 0 equals 0. That math wasn't part of the numeral system.
This brings up a massive practical question. If they didn't have 0 and the numbers are just letters, how do they do math?
This is the key. They didn't do math with the numerals.
What do you mean?
Try to multiply x equal x eighth using just the letters. Try to act it out in your head.
XL times X, L times V. It's a mess. I can't do it.
It's practically impossible. The numerals were not designed for calculation. They were designed for recording.
So how did they calculate the budget of the empire?
They used an abacus, or a counting board.
Explain the setup.
They had a board with grooves in it. One groove for ones, one for tens, one for hundreds. And they had little pebbles. In Latin, the word for pebble is calculus.
Hence, calculus. Calculate.
Exactly. To calculate literally means to move pebbles around. So you would do the math physically moving beads or stones in columns. When you were done, you'd look at the board, see the result, and then write it down using Roman numerals.
So the numerals are just the receipt. They aren't the calculator.
Perfect analogy. The numerals are the save file. The abacus is the processor.
That explains so much. But the abacus brings me to the next big surprise in the research. Fractions.
Yes. The lost world of Roman fractions.
We assume Roman numerals are integers only, 1, 2, 10. But you can't run an economy on whole numbers. If I'm selling grain, I need to sell half a bushel.
Right.
If I'm taxing land, I need to tax a third of an acre.
And this is where the Roman system is arguably better, or at least more practical, than our metric system for physical trade.
Better. That's a bold claim. We love our decimals.
We do. We use a base 10 system. It's great because we have 10 fingers. But mathematically, 10 is a bit annoying.
How so?
It's only cleanly divisible by 2 and 5.
Yes.
That's it. If you try to divide 10 by 3, you get 3.3333, an infinite mess. If you divide by 4, you get 2.5, also messy.
Okay.
Now look at the Roman system. They used a base 12 system for their fractions, a duodecimal system.
Why 12?
Think about the factors. You can divide 12 by 2, 3, 4, and 6 cleanly, no remainders. If you are a pizza shop, you can slice a 12-slice pizza for 2 people, 3 people, 4 people, or 6 people, and everyone gets the same amount.
That is incredibly versatile for trade.
It is. So their main unit of fraction was called the uncia, and uncia was 112th of the whole.
Uncia, that sounds familiar.
It should. It's the etymological root of the English words ounce and inch.
No way.
Yes way. An inch is 112th of a foot. An ounce is historically 112th of a pound. It all comes from the Roman uncia.
Wow.
We are still using Roman math every time we use a ruler.
That is a direct line from ancient Rome to the ruler sitting on my desk right now. That is wild.
Like it connects us directly. So in Roman notation, a single dot was 112, 2 dots was 212, or a sixth, 3 dots was 312, a quarter, and they had names for all of these.
So if I wanted to write 512,
you would write 5 dots, and often they would arrange these 5 dots in a specific pattern. Imagine the face of a die. A dot in each corner and one in the middle.
the classic number 5 on dice.
That pattern and the value 512 is called a quincunx.
Quincunx. I've heard the word quincunx used in literature or design, but I never knew as a fraction.
It's a beautiful word. And the Romans had symbols for all combinations. They also had a symbol for half,
Which was?
the letter S. S stood for semis, which means half. So if you saw V's, that would be 7.5.
Okay, that's simple enough. What about smaller fractions? Say 7.5 plus another 12.
You would write VIIS, followed by a dot. S dot, that's 712ths. 6/12ths plus 1/12th.
It seems complicated to learn, but once you know it, it's actually very precise for physical goods.
It's extremely practical for a non-digital world. You're measuring weight, length, volume. Base 12 is superior in that context.
So we have fractions, we have the zero issue resolved, but what about going big? I mean, really big. The standard chart ends at M for 1,000. If you write MMMCMXCIX, you're at 3,999.
Right.
That's the ceiling of the school numerals. How do they count the budget of the empire or the number of soldiers in a massive campaign? They must have had numbers bigger than 4,000.
They absolutely did. And this is where the system starts to look like secret code or ASCII art. They developed extensions to the notation to handle scaling up.
Walk us through the apostrophist method. That sounds complicated.
This goes back to that curved symbol for 1,000 I mentioned earlier, the CI followed by a backward C. It looks like a C, an I, and then a C that's been flipped backwards. Kind of like parentheses, I.
Okay, so brackets around an I.
Right. That meant 1,000. If you wanted 10,000, you added another layer of brackets.
Yeah.
So like CCI followed by 2 reverse Cs.
It's almost like wrapping the number in more and more layers to multiply it.
Exactly. It's a bit complex to visualize, but essentially they use these curved bracket shapes to denote powers of 10.
It feels very programming-ish, like nested functions.
It is. But there was a simpler method that became popular later called the vinculum.
The vinculum sounds like a Harry Potter spell.
It does. Vinculum basically means bond or tie in Latin. In math, it refers to a horizontal line drawn over a number.
An overbar.
Yes. If you take a standard Roman numeral, say V5, and you draw a line over the top of it, it multiplies the value by 1,000.
So V with a bar is 5,000.
Correct. X with a bar is 10,000. M with a bar would be 1,000,000.
That is so much easier than writing M 1,000 times.
Much easier.
Yeah.
And if you really needed to go massive like hundreds of thousands, they sometimes used a 3-sided box, a line over the top and lines down the sides. That can multiply by 100,000.
So they had the tools. They weren't limited to 3,999. That's just a limitation of the standard chart we teach kids.
Exactly. The system was expandable. It just wasn't standardized. Different scribes used different methods. Some used the brackets, some used the bars. It was a bit of a free-for-all.
Which brings us to the inevitable question. If the system was chaotic, lacked a true zero, and had competing methods for big numbers, why did it last so long? And why is it still here?
The survival of Roman numerals is a story of cultural inertia and prestige. When Arabic numerals, the 0 through 9 we use today, arrived in Europe around the 11th century, they didn't just take over immediately.
I assume because they came from the Islamic world via Al-Andalus and Spain, there might have been some cultural resistance.
There was definitely that, but also bookkeepers and accountants were suspicious of them.
Suspicious of the numbers.
Think about fraud. If I owe you money and I write a promissory note, in Arabic numerals, if I write 100, it is very easy for you to add a 0 to the end and make it 1,000.
True. Or change a 1 to a 7.
Or change a 0 to a 6 or a 9 with a stroke of a pen. But Roman numerals, they're structural. CMV. They are harder to alter without it looking obvious.
Oh, interesting. So Roman numerals were seen as more secure.
Harder to forge. In fact, in medical prescriptions, doctors used Roman numerals well into the 20th century. And they had a specific trick. If they wanted to write 3, they wouldn't write 3, they would write T.
AJ at the end.
Yes. A terminal J with a tail. That prevented anyone from adding another I to the end to up the dosage.
That is a fantastic detail. The trailing J as a security feature.
Right. So for legal and financial documents, Roman numerals held on because they felt permanent and secure. But eventually the math won.
Right?
You can't do calculus with Roman numerals.
No, but they didn't disappear. They just migrated. They moved from being a tool of calculation to a tool of what?
Decoration?
Decoration, gravitas, and hierarchy. That's their modern niche.
Let's talk about gravitas. We use them for kings and queens. Queen Elizabeth II, Pope Benedict XVI. Right. Regnal numbers. It implies a lineage. It links the current leader back to ancient history. Elizabeth II, with an Arabic 2, looks like a sequel to a movie.
Yeah. Wow, thanks.
Elizabeth II looks like an institution.
It does. It looks serious. Same with cornerstones on buildings, built in MMXX. It feels like it's meant to stand for 1,000 years.
That's the cultural gravity of the numerals.
Right.
They signal to the viewer, this is important, this is history.
And then there's the Super Bowl.
The Super Bowl is the ultimate modern example of this. The NFL uses Roman numerals to make the game feel epic, gladiatorial.
Except for that 1 year.
Super Bowl 50.
The year the system broke.
The year aesthetics won over tradition. Super Bowl L. Just the letter L.
L is universal slang for loser now. You can't have the Super Bowl loser.
Exactly. It looked weird. It wasn't symmetrical. So for that 1 year, the NFL switched to Eric 50, and then immediately went back to LI 51 the next year. It proves that we use these numerals primarily for how they look, not just what they count.
We also see them in science, which surprised me.
Yes. Chemistry. Oxidation states, iron 2 versus iron 3. It distinguishes the charge of the atom. It's a very specific technical use, but it's standard. And the periodic table group numbers used to be Roman, though that's changing.
In music theory.
Oh, huge in music. Chord analysis, the I chord, the 4 chord, the V chord. Every musician knows what a IVV progression is. Writing 1, 4, 5 just doesn't look the same on a sheet of analysis.
So it distinguishes function.
Exactly. It distinguishes the function of the chord from the specific note numbers.
It's amazing how deeply embedded it is. We talked about clocks earlier, but even graph quadrants, quadrant 4, 2, 3, 4.
It's a way of separating meta information from data. If your data is in Arabic numerals coordinates, values, you label the structure of the quadrants in Roman numerals to avoid confusion.
That's a great way to put it. Roman numerals have become the labels of our world, while Arabic numerals are the content.
That's a perfect distinction.
So as we wrap up this deep dive, I'm left with a totally different appreciation for MMX660. It's not just a pretension, it's a survivor.
It is. It's a survivor from a time when numbers were physical fingers, notches, pebbles. It's a system that refused to die because it adapted. It bent the rules. It integrated with language.
And it's still breaking rules today.
It is.
I want to leave our listeners with a challenge. The next time you see a Roman numeral, whether it's on a clock, a copyright date at the end of a movie credits, or a chapter in a book, look closer.
Check the 4. Is it 4 or the 3? Check the date. Does it follow the subtractive rules, or is it doing its own thing?
And remember that for every nice, neat M or C you see, there's a history of shepherds, soldiers, and rebels who decided that sometimes writing Ajax just made more sense.
The map is not the territory, and the rule book is not the history.
Exactly. Thanks for diving in with us. We'll see you in the next one.
MMX7.
Maybe. Catch you then.